Today we have to do probability. And probability isn't actually very common. It isn't very common in the kind of statistics that we're concerned with. So this is just the basic stuff, and there's, at the end, we do conditional probability, which is probably more important to you. But this is just plain, what's the chance that something happens? And they make a distinction between classical probability and empirical probability. Classical probability is something that we know, like flipping a coin is 1/2. You roll dice, it's 1/6. Empirical probability is the chance that it's going to rain. Nothing hinges on classical probability except if you go to a casino and you're betting on a roulette wheel or you're dealing cards. The chance of a particular set of cards is well known or easily known. The important things, we can't actually make a good probability. We can try. But this is just what's the chance that one event occurs out of all the possible events that can occur. So if you flip a coin, you get heads or you get tails, and it's pretty much 1/2. You roll dice, you get a 2, you get a 3, it's 1 out of 6 for each one of those things. The only thing that confuses these is the way they're expressed. And one way is an odds ratio. And this is like betting on a horse. If the odds are 2 to 1, that means if the race is run 3 times, they expect the horse to win twice. So you add those two together, and that's the setup. So that's an odds ratio, and a lot of things are done as odds ratios rather than as a strict probability. This is sample space. And the probability is the chance that the event occurs out of all the possible ways it can occur. The sample space is all the possible ways the events can come out. For one coin, it's heads or tails. That's the sample space. That's the way it can come out. For 2 coins, we have a different deal in that you can get heads on one, tails on the other, and some combination of those things. So we can get a head and a head. We can get a head and a tail and a head and a tail and a tail, which that is not. So that's the sample space for flipping 2 coins. And the chance of getting a head twice is 1/4. The chance of getting anything, any individual one, is 1/4. So there's 4 ways that this can happen, and that's the chance that it occurs. If you go to 3 coins, you just have all possible combinations. This isn't something you can really do. The chance that it's going to rain. They say there's a 20% chance of rain, which apparently means there's a 20% chance of rain somewhere in the area that they're talking about. But it's not like there's a 20% chance that it's going to rain right here. Some things are. This is what happens when you roll 2 dice. All right, you ever play craps? If you go to a casino, there's a crap table. You've seen them. There are people shaking dice and they're rolling them, and they've got the people at the end, and they're scooping up the dice with a stick and all of that. Basically, you roll 2 dice, and you get the sum of the faces on the dice. And that's your point. So that if you roll 2 3s or 2 and 4, you get a 6. That's your point. And then you roll again until you get your point again. And if you get a 7 or an 11 before you get your point, you lose. Also, if you roll a 7 or an 11 first time, you lose. You get your point. This is the number of ways this can come out. Here's 1 and 1, 1 and 2, or 2 and 1. That can happen 2 ways. 4 is 1 and 3, 3 and 1, or 2 and 2, which is 3 ways. 5 is 1 and 4, 2 and 3, 3 and 2. I forgot what I was getting. But there's 4 ways, and so on. And this comes up to be 36 if you add all these things up. So if I have a 6 as my point, what's the chance that I'm going to get a 7 or an 11 before I get 6 again? Is a 7 or an 11 2 plus 6 is 8 out of 36. What's my chance of getting another 6? And that's just 5 out of 36. I have a much greater chance of losing than I do of winning. If I roll what I want to roll a 6 or a 5. If I get a 7, I lose, so I want the highest chance of each of these. If I got a 6 and 6 the first time, I'm toast. It isn't going to happen because there's only a 1/36 chance that it occurs. These things are how this comes out in practice. That's the basic idea of probability. Some of the things that are important, one is the complement. And if I want to know what the chance of rolling everything but a 12 is, the easiest way to find out is to find out the chance of rolling a 12 and then subtract it from 1. So the complement is the other end of it. And all probabilities have to add to 1. If they don't add to 1, it's not a probability distribution. Other things, or and. If I have an or, it's I get this or I get that. I toss a coin, do I get heads, or I roll a dice and I get a 6. Or means add. So the chance that I get a head is 1/2. The chance that I roll a 6 with 1 die is 1/6. Those two added together is the or chance, this or that. If it's and, it means multiply. These things come up later when we're doing particularly the binomial distribution, and they just happen. They're in passing. They're just embedded in it. That's why it's important that you hear the or and the and. So or means add, and means multiply. If I want 1/2 for a head and 1/6 for a rolling a 6, that's 1/2 times 1/6. And it's much less likely. I've got 1/2 times 1/6 or 1/12 of a chance that this will occur. One important thing, and this comes up a lot in statistics, are independent events. I'm pulling cards out of a deck. What's the chance that I get a king out of a deck of cards? 4 out of 52. I pull out the king and I put it back. What's the chance that I get a queen on the next draw? I put the king back, 4 out of 52. Now I take the king, first draw, and I don't put it back. Now what's the chance of getting a queen? How many cards have I got left? Took out the king. I got 51 cards left. Now it's 4 out of 51. So those things aren't independent. If they're independent, the probability of one doesn't affect the probability of the other. And this comes up in basically overlap. The probability of E or F is the probability of E plus the probability of F, or means add. And if they're not independent, I have to subtract the probability of E and F. So that if I want the probability of someone with a hat in this whole building and someone with a size 8 shoe, I've got all the people with a hat, probability, all the people with a size 8 shoe, but I have to take out people that have a hat and a size 8 shoe. This is the classic Venn diagram. So the probability of E or F, when they're not independent, is this area plus this area, and I have to take out the overlap. So it's minus. The idea of independence is much more important than the Venn diagrams or any kind of calculation. Independent events, it's a whole different game. Dependent events, it gets chancy. Right, like the chance of rain. The chance of rain isn't independent of the chance of moisture in the air, chance of temperature, etc., etc., etc. That's why it's so hard to predict the weather, because it depends on all kinds of things. So that's why statistics is bets. It depends. We don't know. All we can do is bet. Independence is something you want to keep in mind. All of this stuff is best done with contingency tables. And this is a 3 or a 2 by 2 contingency table. Here I have a dog or a cat. Do these people have a dog or a cat? 30% have both a dog and a cat. 20% have a cat but no dog. This is where the big weather models come in, except they have a matrix that's got thousands of variables and thousands of different possible combinations. And it takes a really big computer to run the models. So this is 2 by 2. I could have another dimension. Back here, do they have a horse? So a contingency table is much more important and is the easy way to do probabilities. But here, the probability of having a dog and a cat is not independent. So that if I want the probability of a dog, these are called marginal totals, marginal distributions, because they're on the margin. So that there's a 45% chance that someone has a dog, regardless of what cat status is. The probability of no dog is 55%, and those things have to add to 1. The probability of a cat is 0.52. The probability of no cat is 0.48. I want the probability of a dog or a cat. I have 0.45, probability of dog, 0.52, the probability of a cat, and I have to subtract the probability that they have a dog and a cat. Otherwise, I'd be counting them twice. And this is the way life insurance works. You smoke, you don't smoke. You've had a heart attack, you haven't had a heart attack. You exercise, you don't exercise. Or you exercise a little. So there's dimensions going everywhere on a contingency table. What you can do with anything is make a contingency table. This one, we have ice cream preference, chocolate and vanilla, whether they are children or adults. What's the chance that if I pick someone at random, I get a child that likes chocolate ice cream? There's 57 here out of a total of 191. So the chance is 57 over 191 that I have a child that eats chocolate ice cream. What's the chance of a child in my group? Regardless of ice cream preference, here I have 85 children. So what's the chance that I get a child? It's 85 over 191. What's the chance that I get a child that likes chocolate, a child that likes vanilla, an adult that likes chocolate, an adult that likes vanilla? What's the chance that I get a child that eats chocolate and a adult that eats vanilla? It's and 57 out of 191 times 63 out of 191. So I can get all of these things out of a contingency table. I can do this as percentages. I can convert all of these as a proportion of 191. And I get all of this stuff in here. And you can make a contingency table I have two events, A and B, and I can have not A and not B. If I have A, I have a not A. If I have B, I have a not B, and I can make a contingency table out of this. Here's A and not A. Here's B and not B. If I have any three probabilities, I can complete this table. Say probability of A is equal to 0.35. That goes there. That's the probability of A unaffected by B. What's the probability of not A? All probabilities have to add to 1. It's A and not A. I need a 1 there. What goes in that spot? So the probability of not A is equal to 0.65. 1 minus 0.35. So the probability of B is 0.6. What's the probability of not B? 1 minus the 0.6. Now, I have to have something inside. All I need is one thing inside. This cell is the probability of A and B. This cell is A and not B. This is not A, not B. Both of these are ands, or all of them are ands. A, B, and not A and B. If I know any one of these things, and one here and one here, I can fill out the table. And this is where's that damn homework? Suppose that 33% of people own dogs. If you pick two people at random, what is the probability that they both own a dog? And means multiply. So it's 0.33 times 0.33. The more ands you add, the less probability you have. Where is it? Come on. Now I very carefully check this out. Yeah, heck with it. The probability of A and B is 0.1. Just made it up. Now, I have A, not A, B, not B, 0.35, 0.65, 0.4, and 0.6. That has a 10% probability. What's the probability of not A and B? It's got to add up here. That's 0.5. What's the probability of A and not B? 0.1 and 0.35, that has to add. And the last one, not A, not B, is 0.15. All of these things have to add up. And if you ever have a problem with a contingency table and it says use a Venn diagram, don't. Do this. So here I have a probability of A, a probability of B, and a probability of A and B. And I want the probability of B given that A has occurred. Probability of A is equal to 0.72. The probability of B is 0.18. And the probability of A and B is equal to 0.1. So we have probabilities and we want to make a contingency table. So the probability of A as not A, B, not B, .72. That's the probability of A. What's the probability of not A? 1 minus 0.72, 0.28. Probability of B is 0.18. That's this entire column, probability of B, regardless of A. Probability of not B is 1 minus 0.18, which is 0.82. Now we have this one cell, A and B, and we can figure out the rest. We're given three things, two marginals and one in the table. Fill out the rest of the table. A and not B. Not A and B. not A and not B. And it has to add across and down, and this has to be 1. So there's the contingency table. Now, conditional probability. What did they have on this problem? B given A. What's the probability that B occurs given that A has occurred? Where is A? Probability of A is 0.72. What's the probability of B within A? And we can do these with numbers or with proportions, so that the probability of B, given that A has occurred, restricts me to that one row, the A row. And I can do this for any one of them. The probability of A, given that B has occurred, I go to this column, probability of B, and this is the probability of A within B. So this is 0.1 over 0.18. The probability of B is small, smaller than the probability of A, and compared to not B. But once I'm in B, this has a very likely chance of happening. So that a conditional probability is much stronger than just plain stuff. The problem is now I've got a matrix that's 1,000 by 1,000 by 1,000 by 1,000 by 1,000 by 1,000 minimum. And I want to do this kind of calculation in that kind of huge multi-dimensional mess. That's why it takes such a big computer, so much computing power to do these things. We can do these for this kind of stuff. But if you have something real, it is much, much more difficult. Here, we're back to ice cream and children and adults. What's the probability that you get a child given that they like chocolate? Child given chocolate. Given restricts you to chocolate. So I'm in here, I have 57 out of 100. So I have a 0.57 chance. What's the chance that I get an adult given that vanilla is the choice? Given vanilla, I'm in here, adult is 63 over the 91. So any one of these things I can do. And this is where you get the people who run election supporting a candidate. They're working for someone. They want to go and identify people who will support their candidate, and then they want, what's the probability that that person will vote? And that's why they make so much voter effort. Given that they will support their candidate, what's the probability that you can get them to vote? And if you can raise that probability, you can win any election. Most elections aren't won by votes, they're won by people who don't vote. That's why voter turnout is such a big deal.